All right, I think I had the camera up. I don't know where it is. I'll probably have it closer. Okay, so there we go. Lecture 4. And this should be page 23. All right, so today we're going to look at how to use the indicial notation to determine the determinant. So determinant of a matrix using indicial notation. Okay, so basically what we did before is what? To calculate the cross product using the matrix form and then using the indexes. So we can do something similar to determine the determinant. Let's see if that's a little bit better. So let's say for a 2x2 metric, because it's always easy. That's why I said yesterday that wait until today's class to have the answer to that question. Is this case over here. So we do the determinant, let's say of a matrix which is 2x2. The general notation for the determinant is you put the vertical lines and the letter in the middle, and your matrix will have coefficients A11, A12, A21, A22. So it's well known that the determinant will be equal to what? A11 times A22 minus A12 dot A21. Okay? But actually we can rewrite this in indicial notation as follows. So or in indicial notation we'll have that the determinant of the matrix A will be equal to epsilon ij, A of 1I, A of 2j, okay? And here, our little wheel over here is 1, 2 will be positive just between 1, 2 and 2, 1 will be negative. So that's what I'm saying. You see that for 2D, you can actually eliminate one of the indexes, no? So I think it makes it a little more clear. You have ij, if it's 1, 1, 2 will be positive, but if you have 2, 1 will be negative, all right? So if we do this here, the calculation, what you're gonna have if you start switching this, you're gonna have, let's say you put epsilon first, 1, 2, what will you have? I is 1, j is 2, so you'll have A of 1, 1, A 2, 2, okay? Plus, now you switch the order, epsilon to 1, this will give you A 1, 2, A 2, 1. And if we follow the same logic that we did before, 1, 2, because go clockwise, this should be positive. And because here the order is reversed, for this Levi-Civita operator, this one will be negative. Okay, so it's the same case as before. What happened is that I remove one of the indexes, okay, for 2D. So this will give you actually exactly the same result as previously as over here. This will give you what? A11, A22 minus A12, A21. Okay? Obviously as expected. Okay, so we did the 2 by 2 matrix. So let's say here 4, a 3 by 3 matrix. Basically, we should have something similar. So we have determinant of A 3 by 3 will be equal to the determinant of A, and this time you will have what? A 1 1, A 1 2, A 1 3, A 2 1, A 2 2, A 2 3, A 3 1, A 3 2, A 3 3. So basically on the homework, I'm going to update it. What I'm going to ask you is to do this. Calculate, let's say, a determinant of 3 by 3, okay? Using your own Levi-Civita operator, all right? So if we expand this on the matrix form, this will be equal to what? Okay, looks like I'm going to break it. So if we look at the matrix over here, this should be equal to A11, A11 factor of what? A22 times A33 minus A32 or minus A23 times A32. Okay? Now we switch the sign, minus A12 factor of so this one will give you A12, A21, A33 minus A23, A31. All right? Plus A13 of A21, A32 minus A22, A31. So basically, if we expand now the terms, this will give you what? Okay. A11, A22, A33 minus A11, A23, A32 minus A12, A21, A33 plus A12, A23, A31 plus A13, A21, A32 minus A13, A22, A31. okay, or using Indicial Notation, the determinant of A 3 times 3 will be equal to what? Epsilon ijk A of 1I, A of 2j. So this would be like if it was 2D, but because it's 3D, we need to add A of 3 sub k. Okay, so let me do the same figure as the other day. So for the permutation operator, the Levi-Civita, the same thing I did the other day. You have here I, J, and K, and let's see, you have here the different permutation you can have is 1, 2, 3. I mean, when I do this here, okay, so let's say it would be 1, 2, 3, 2, 3, 1, or 3, 1, 2. 3, 1, 2, or these three should be the positive ones, no? Same figure as last time, okay? Now, we can do the reverse, so you have 1, 3, 2, okay? Then you have what? 2, 1, 3, and the last would be 3, 2, 1. And these three permutations should be net. So hopefully we have space over here. So if we use this equation here, now we substitute into this one, okay? So let's go following this order. First one will give you what? Epsilon 1, 2, 3. Then you have A 1, 1, A 2, 2, A 3, 3. Okay? And this over here, the Levi-Civita operator will be positive 1. Okay? So this term will actually represent this one. Okay, the one over here. Maybe I'm not following the exact order. Now let's follow this one plus epsilon 2, 3, 1. This will give you what? A 1, 2, A 2, 3, A 3, 1. And again, this one will be positive. And this one will correspond to which one? This term over here. Okay? So basically we have the same thing. All right, so let's keep going. Plus, I'm not gonna space here, plus epsilon, we'll do the third one, 3, 1, 2. So it will be A of 1, 3, A of 2, 1, A 2, 3, 2. And again, this one will be the last case of positive. So if this one is the positive, this one the positive, this one should be this one, no? A1, 3, A2, 1, A3, 2. Okay, the three positives are the same. Now, obviously, we're gonna have the three negatives. That should be the last three cases. So plus epsilon 1, 3, 2 would be A of 1, 1, A of 2, 3, A of 3, 2. And we know this one will be negative. And if we compare to this one, this will compare to the second term. All right? So 2 more plus, now we do this one, 2, 1, 3. So it'll be epsilon, A 1, 2, A 2, 1, A 3, 3. This term will also be negative, and this corresponds to A12, A21, A33 to this term over here. And finally, we have plus epsilon of 3 to 1, A of 1, 3, A of 2, 2, A of 3, 1. This one should also be negative. And that should correspond to A of 1, 3, A 2, 2, A 3, 1 will be the last term over here. Okay? So basically you get the same thing. All right, so now that we did the 2 by 2 and the 3 by 3, we can expand this equation here to any n by n matrix. So for an n times n matrix, okay, the determinant of A of n times n equals to n of A would be equal to the epsilon ij depending on the dimension. So if it's 2D, you only need 2. If it's 3D, you need 3. If it's 5D, you need to put 5 sub-indexes, no? Okay? Of A of 1i, A of 2j, and you will go like that until A of n k. All right? Will be the same thing. All right, so now we're going to look at a new operator. So we're going to look at the epsilon delta. So epsilon delta identity. So the epsilon delta identity is defined as, so here pay a bit of attention, so you have epsilon ijk times epsilon imn. So here the trick is always need to put the first one the same one, okay, of the order, and this is equal to delta jm. Now I'll tell you how this is done. Delta km minus delta jn delta km. So over here, I is the repeated. So the I is defined as the dummy index. Okay, here, be careful with the notation. This is, we'll find out the answer. This is JM, this is KN. Okay, it's an N over here. So the way it works is, what you do over here is this, is that for the first operator, for the first term, okay, let's see, how can I do this? All right, let me put over here, J, let's see if this might make it clear. J, K, let's put here the I, M, N. But this one is the dummy operator, so it just stays over here, okay? Okay, really, to make it simple, the first thing you do is you look at this one. So the I, you neglected, and the first thing you need is to combine the J with the N, and you combine the K with the N. Okay? So for the first term, you're going to combine the J with the M. All right? So as you see, the first one, second one, third one, no? The K with the N, this would be for the first term. And now for the second term, what you do is actually you switch. You take the second term and you're gonna add it to, and you're gonna combine it with the third one. All right? For the second term, you're gonna have then J and over here. And the one will be what? The third one with the second one. So it will be K and M. So this will be the second term over here. So this is the first term. And here that would be the second term. All right, so let us do some examples. So the first example we're gonna have is example. Show that epsilon J K Q epsilon M K Q equal to 2 delta JM. Okay, so over here you see, we can leave, as an example, we're gonna leave the Q at the end. All right, so this will be our dummy index, no? Okay, so here we can come, let's just rewrite the same line, epsilon J K Q epsilon M K Q. Well, actually you could choose over here because you have two repeated indexes, no? K and Q. But let's say here we choose Q as our dummy index, okay? Then what do we get? We get, we eliminate Q, we get the first one with the first one. So it will be Jm, okay? Delta Jm. Then we do the third one, that will be delta Kk minus, now we're gonna switch, we're gonna have delta of K, no, sorry, delta of J K times delta of K M, the first one. You want to give you a few seconds to digest this, okay? You see, this one is at the end, but it could be at the beginning, all right? So I did this one with this one, times this one plus this one, and now I switch. I do this one times the K plus the K times the M, all right? So this will be equal to what? We know this is equal to delta Jm. And on a previous problem, what did we say was this? IKK would be equal to delta 1, 1 plus delta 2, 2 plus delta 3, 3. And each one is equal to 1. So all this term is equal to 3. Remember what is the definition? If I equal j is equal to 1, if I is different than j is equal to 0. So you have kk repeated, this is equal 1 plus 1 plus 1. All right? So we have this minus so let me maybe not go too fast. What will be this term over here? Will be, this is the K, no? So this could be written as Jm. All right? So at the end, what do we have? This is equal to 3 delta Jm minus the delta Jm, which is going to give us the 2 delta Jm as required. All right, so let's do another example. Okay, so the other example is to show that epsilon j kq epsilon j kq is equal to 6. All right, so let me just write over here, epsilon j kq, epsilon j kq. So over here, what is our dummy index? Anyone, really. So which one you want to use? We can use, maybe let's use j, no? Since the first one. All right, one, let's say j dummy index. We take that one as our dummy index. So now what do we need to do? The first one will be second one with the second one. So delta kk, delta qq. And now we just need to inverse this one, will be kq and qk. So basically, same as before, this will give us delta KK delta QQ minus delta, since we use, whatever you want, this will be delta KK. Okay? So now, from your question before, how many we have? 3, no? So this will be equal to what? Delta 1, 1 plus delta 2, 2 plus delta 3, 3 times delta 1, 1, delta 2, 2, delta 3, 3 minus delta 1, 1, delta 2, 2, delta 3, 3. Because we have 3 indexes, we know this would be equal to 3. This will be equal to 3. This will be equal to 3. So basically at the end, what you have, 9 minus 3, which is going to give us that the epsilon JKQ, epsilon JKQ is equal to 6 as requested. All right. So I know we already did it, we already talked about it, but we're just going to look at it again with this new notation, okay, with the epsilon Kronecker operator. Would be what? We're going to look at the triple cross product. I know we already look at it, but it's going to change it a bit now with this notation. I mean, just one line, just one additional line. And it's practice, anyway. So what is the triple cross product? So remember, when you do the cross product, it's important to know which one you need to do first, no? So here, let's say we do this one here. So what I'm trying to say is that if you put the parentheses before U and V is not equal to this one, because you change the order in which you do the operation and the result will be different, no? Okay, so here the parentheses are important. So if we do this with indicial notation, not with the matrix notation, these are 3 vectors. So each vectors we have magnitude and directions. We have U sub I, E sub I, cross, let's say, V of J, E of J, cross W of K, E of K. All right? So again, this will give us U of I, E of I. We do first this one over here, so it will be cross. This one, what do we need to do? We have indexes J, K, and let's call the JK, okay, I have Q on the notes. We can change it if you want, but let's say Q. This will give you what? V of J, W of K, and this will be E of Q. You know where the E of Q is coming, no? Is the E J cross EK, no? Should be a perpendicular one. All right, so we did this one. Now we need to do the other cross product. So this one will be between what? I and Q, no? So this will give us here. Let's see, we have epsilon I Q, and let's call the new one M. The other ones stay unchanged. Epsilon J K Q of U sub I, V sub J, WK, and now we have EI cross EQ. That should give us EM. All right? So now, You see here the index is now, we need to put the same index at the same location. So we need to put the Q at the same location, no? So let's say we're gonna move the Q, since this one is at the end, probably move this one to the end. Okay, might be, instead of moving all of them somewhere. So this will give us what? So it will be equal to epsilon then, if to follow the order would be M IQ, yeah? Epsilon J KQ, U sub I, V sub J, W sub K, E sub M. So in this case, our dummy index will be Q. If we use Q as the dummy index, what do we have? Remember, we need to combine the first one with the first ones will be delta M J, the second one with the second one, so I K minus, now we switch the order, will be delta of the first one with the second one will be MK delta of IJ. Of U sub I, V sub J, E of M. Okay, I mean, it really doesn't matter if you do it this way or this way, but I just want to say you can transform now these two operator by the two epsilon by these two delta Kronecker, no? To see the relation. All right, so the typical problems you have in this class, we're going to do one now, is to demonstrate that one relation is equivalent to another one. So let's do another example. Yeah, maybe for the first example, I'll go very slow. So in this example, you need to show that A cross B cross C is equal to A dot C times B minus A dot B C. Okay? So basically what it says is that to do in the triple cross product is equivalent to do this operation over here. Okay, and you need to prove it. All right, so let's go slowly, but let's do it. All right, so as before, here you can either start from this end and come into this side, or you can come to this side and end up with this expression, no? Which is what we're gonna do over here. We're gonna start from here and we're gonna prove that this is equal to this. So basically it's the same thing that we have done now, identical. And the only thing we need to do is on the last step to see what will happen with those. Basically it's identical to this. Instead of going UVW, we call it ABC, but then we need to see what happened with this expression, no? Okay, but let's just redo it, it will be practice. So this will give you what? A cross B cross C is equal to what? So this is a vector A of I, E of I, cross B of J, E of J, cross C of K, E of K. All right, so this gives us A of I, E of I, epsilon of J, K, Q, let's call it BJ, CK, and this will give us now EJ, EK. This becomes what? E of our new index, which is Q. All right, now we do the first cross product. Let's call that one. So we have I and Q. So we have I, Q, M. We use the same as before. Epsilon, J, K, Q. A of I, B of J, C of K. We do E sub I cross E sub K, and this should give you the E sub M. So exactly the same thing as before, okay? Now we use the relation to go from the epsilon to the delta chronometers. So in this case, okay, we need to do the same thing. We need to move the Q. So you want to move it at the end or the beginning. All right, let's do the same thing as before. So this will be epsilon M I Q epsilon J K Q A of I, B of J, C of K, E of M. It's exactly the same thing as before. So now this is equal to what? Q is our dummy index. All right. We're going to have delta M J delta IK minus delta M K times delta I J. And this remain unchanged. A of I, B sub J, C sub K, E of M. Okay, so now there's two ways to proceed from here. I don't have to show you both of the one I generally do. I'm going to show you the one I generally do, okay? And then I'll show you one on the page, the other one, and if you want, we can do it. If you don't want, we cannot do it. But basically, what do we get from this figure? This figure, these two terms over here, the only way that it will be different than 0 will be if J, let's say, equal M or M equal J, no? And K equal I, all right? So that would be our first case. So that would be our first case. And the second case will be what? This will mean that K, doesn't matter, you can change the order, but K equal M or J equal I, no? Yeah. So that's what we do now. So what you do now is that, so I'll give you the first one. This will give you what? Here we do the first time will be, so we can do A of I, we keep the A of I, we do this one, okay? With those indexes, J equal M or K equal I or I equal K, doesn't matter. Then we have BJ, but the J will be equal to M, so it will be BM. All right? And we know that K needs to be equal to I, so it will be CI, and then we'll have here the E of M. So it will be for the first term. Now the second term will be equal to what? Minus, we have a sub I again. Now j needs to be equal to I, so we have b sub I. And the last one will be k equal to m c of m. So basically you need to end up with the 3 times indexes over here, no? Or the same ones. And this would be E of m. So now, if you remember the definition of the dot product, what was the definition of the dot product for using the indicial notation? It was A of I times A of I, no? You do the square. So everyone that had the sum index will be here a dot product, so it will be equal to A dot C because the same index. Okay, this is the dot product. Times B, which is the one with a different index, minus what? Which one now are the ones that have the same index? Will be AB. So A dot B times C. Okay? Which is what? Exactly what we need to prove, no? Okay? Maybe let me do something here for consistency that I see. In this one, I put vectors, so if you want, let's put vectors everywhere. Because on one side I put vectors, the one I did not put vectors. And here I did the same thing. Just for consistency on the notation. Okay, so that's generally the way I do it. If you want the other approach, I can show it to you. And if you want, we do it, okay, in the class. It's like this one. You see, before, instead of doing it here, I put each one of the terms with the IK and JM, and then I see what you need to do with each one of them. You want to do it? Let's just do it, okay? Since it's the first time. Or what you could do is what? Or you could have proceed as follows. So basically, once we get to this line over here, so the delta mj delta ik minus delta mk delta ij, a of I, b of j, c of k, e m. What you can do is this. All right, so over here, you see IK has 2 indexes in common, no? Yeah? So you could say this is delta. You should have stopped, you can start by the other one, but IK of A of I C of K. Then you look at the MJ, will be the delta MJ. This term should go with the BJ, okay? And this should be E of M. And now for the second term, you can do minus. So let's look at what? Let's say the delta ij, because you have 2 repeated, delta ij. What are the 2 repeated? A sub I, B sub j. And now would be the other one, delta mk C sub K EM. So now, when you look at this one, what can you say about this one? K equal to I, J equal to M, J equal to I, and here you could say that K equal to M, no? So then what do you get? You're gonna get then I sub I, C sub I times BM of E of M minus A sub I, B of I times C of M EM. Which basically is the same thing that we had over here, no? Which is A dot C times B. You see, we get exactly that way over here, but just we already combined the indexes. Minus A dot B times C. So I don't know, do you see any difference between both of them, or they look the same to you? They are more or less the same, no? It's just how you want to combine the terms. In this method, you combine them right away. In this method, they might move around, okay? But you can then move them around and combine them. All right. Let's see what time is it. Do we have time to do another one? I think I'm going to stop over here because we don't have time to do the next example. So let me stop here the video.